Hi, and welcome to MSc. In today's lesson, we're going to be looking at an example of a chemical equilibrium where we're going to be asked to find the value of Kc. So here's the example. We're going to be given a chemical reaction below. A plus 2B is in equilibrium with C and 3D. I've kept this example generic. These could be any species at all. And we're asked to determine the equilibrium constant if we know that we had 1 moles of both A and B that were combined with 0.5 moles of substance C in a 1 liter vessel. The 1 liter vessel is key, and I'll clear that up or clarify more in the coming slide. This reaction was then allowed to reach equilibrium at a fixed temperature, and it was determined that the equilibrium concentration of substance D at equilibrium was 0.60 moles per decimeter cubed. So when we're faced with an equation like this or a question like this, we have to set up a chart. And this chart can look something like this, and when we fill in values, we're going to put in values for A, B, and C along these columns, and we're going to talk about their initial concentrations, their changing concentrations, and then their equilibrium concentrations. So initially, we added 1 mole of both A and B. It was key that it was in a 1 liter container because that makes the concentration 1.0. If it was in a 2 liter container, you'd have to divide by 2. So watch for that type of question, just to be careful. So we know that we had 1 mole in a 1 liter container, which makes its initial concentration 1. Same with B. C was 0.5. And this is all because it was in the 1 liter container, right? Because keep in mind that concentration is equal to moles per volume. There was no information about D, so we're going to assume that originally in the vessel there was none of substance D. The change, what we do for the change is we assume here, I like to assume that we're going to shift towards the products. That might not always be true, and it might give us a negative answer that we have to then work with, which is fine. Here we know we can't shift to the left because we have none of substance D. So what we do is we say, okay, well, A and B are going to lose some chemical, and C and D are going to gain. And this is always based on the stoichiometry. So we say, okay, well, the change here, A will lose an X amount, but because it's a 1 to 2 ratio, B is going to lose 2 times X. C has a coefficient of 1, so it's going to gain X, and D is going to gain 3X. So this means that our equilibrium expressions for each of these substances, A will be the one that it started with, the 1 mole per liter, minus X. B will be the 1 mole per liter minus 2X. C will just be, it'll be 0.5 plus X. And D will just be 3X. There we go. So the other piece of information that we know here is that this 3X that D will be is also equal to 0.60. And that was given in the question itself. If you go back to this first slide, it told us that that was the equilibrium concentration that was measured in some manner. So that's where that value came from. So based on this, I can actually calculate X by dividing both sides by 3. I can obtain that X is equal to 0.20. And this is a concentration value. This is moles per decimeter cubed. Okay, so based on that information, I can then go and calculate all of the other equilibrium values. So over here, I can say, well, this is now 1, subtract 0.2. So this is going to be 0.80. And this will be moles per decimeter cubed. I'm going to write that down here as a molarity, M for short form of the moles per decimeter cubed. This one here will be 1.0, and it'll be minus 2 times the 0.2. And so this is going to give a value of 0.60 mole per decimeter cubed. And then C gains, right? So this is 0.5 plus 0.2. And this is going to be 0.70 moles per decimeter cubed. So we have all our equilibrium concentrations now, which means we can sub this into our equilibrium expression. Now, for the equilibrium expression, we have to remember how to write out the equilibrium expression for our equilibrium constant Kc. And we have to go from this, and it's the products raised to their coefficients over the reactants raised to their coefficients. So this equation here will be the concentration of C, concentration of D, and it's going to be raised to the 3 because it had a 3 as a coefficient. The C has a coefficient value of just 1. It will be the concentration of A raised to the power of 1, which was its coefficient, and B squared because its coefficient was 2, which is why there was a 2 here. Okay? And now we can substitute in our values. So the concentration of C is this 0.7. So 0.7. The concentration of D was 0.6. That was given to us at the start of the question. That's cubed. All over concentration of A, which is 0.8. Concentration of B, which is 0.6. And now we can solve. There is some simplification. 0.6 squared. Almost missed it. There is some simplification I can do here. I can do some simplification. It won't matter really if you notice that or not. It could make your life a little bit easier. If you punch this into your calculator, you should get 0.525. Okay? We were working with two significant figures throughout this problem, so I would write this as 0.53. Okay? And that will be the equilibrium constant for this reaction as shown up above here. Okay, so when we already know some equilibrium concentrations, we have to use what's called this ice chart, just like this, where this is my initial, my change, and my equilibrium. And we have to use these often when dealing with equilibrium problems. And if we already know an equilibrium value, I can determine the value of x, all the equilibrium values, sub it in, round appropriately, and there we go. I hope you found this short example helpful. Thank you very much for listening, and thank you very much for watching.